Hi everyone, we are from Group 1 and I'm Dei You Song. The structure we chose for this video assignment is the ironing board. The reason we chose the ironing board as a structure we study is because ironing board is a structure that every household will have, which is very easy to achieve and appears frequently in daily life. Before we go into the structure of ironing board, let us know some terms for this video. Free body diagram are diagrams to illustrate the direction and magnitude of forces that act upon the structure in a given condition. This technique is used for the convenience of having a picture about the resulting forces on the body. In free body diagram, the forces are represented with arrows which indicates the direction of force, and the magnitude of forces are labeled for the particular force acting on the structure. Equilibrium is a condition of a system that is at rest or moving in a constant velocity, which means that summation of force equals 0. When all forces act upon the structure is balanced, the structure will reach the equilibrium. When the body is at rest, the body is in static. In this video, we are showing an ironing board which is in static condition. The moment of inertia, also known as the rotational inertia of a rigid body, is a quantitative measure that determines the torque needed for a desired angular acceleration about rotational axis, and we know that the larger moments requiring more torque to change the body's rotation rate.
Hi, my name is Teh Xin Yu, and now I'll be explaining on the LO1, which is the free body diagram of the static structure. As we can see from the slide here, the real-life example of the static structure our group have chosen is the ironing board. And this is the free body diagram that I have drawn based on the ironing board here. As we can see from this free body diagram, there are several forces acting on it. One of them is the weight of the ironing board, which is acting downwards, and the weight of the ironing board is 49.05 Newton. It is calculated by multiplying the mass of the ironing board, which is 5 kg, with the acceleration of the gravity, which is 9.81 meter per second square. Next is point A, which is a pin connection. The reaction forces are AY, which is the vertical component of the force, and AX, which is the horizontal component of the force. There are also two normal reaction forces acting upwards at each leg of the ironing board. The direction of this normal reaction force is opposite with the weight of the ironing board. Besides the forces acting on the ironing board, I also consider some measurement of the distance between some points. One of them is 0.25 meter, which is the distance between point A and the weight of the ironing board. 0.06 meter, which is the distance between point A and the normal reaction force here. And also lastly, 0.59 meter, which is the distance between point A and the normal reaction force here. The calculations of the forces in equilibrium will be further explained in the other slides.
Hello everyone, my name is Aliah, and today I'll be talking about LO2, which is use equilibrium-based analysis for various structures. So the sample problem is find the reactions at A. Given the mass of iron board is 5 kg. So now we can convert 5 kg to Newton by multiplying with 9.81. And here's the free body diagram based on the previous LO1. Now, this is the solution. So we're going to use equilibrium of a rigid body where the external force and moments are balanced. So the resultant force and coupled from all external force are equal to 0 in this system. So Fx equal to 0. So the force exerted on x-axis is only Ax. So Ax is equal to 0. For Fy equal to 0, we're going to look here based on the free body diagram. So there's Ay minus W plus 2N. So Fn is the reaction force. And then we're going to get this equation, Ay equal to 49.05 minus 2Fn. So for MA, there's moment at point A is equal to 0. So 0.06, which is the distance point A from the first end here, and plus 0.25 with the weight. 0.25 is the distance between the weight and the point A. And for this one, we're going to use right hand rule to determine whether it's negative or positive. And then we're going to minus 0.59, which is the distance between this end with the point A, and equal to 0. So we're going to get this Fn equal to 23.14 Newton. And after we already got the reaction force, we're going to plug in into the equation of Ay. So we will get Ay 2.77, and so the reactions on point A is Ax equal to 0 and Ay equal to 2.77 Newton.
I'm Adriana. I'm going to explain my part for LO number 3, employing moment of inertia-based analysis for problem solving. The component that is chosen from the structure is the leg of the ironing board. It actually comprises of two legs that are crossed with each other, but we're just going to demonstrate only one leg. So as you can see, it is assumed that the leg is a U-shaped structure which can be further divided into three rectangles: rectangle 1, rectangle 2, and rectangle 3. And here are the dimensions. First of all, we have to determine the first moment with respect to x and y axis and the centroid of the whole structure. By looking at it, we can actually obtain the x-coordinate of the centroid, which is half of the horizontal distance here. Because if we put a vertical line here, we can see that the structure here is symmetrical. But we're going to compute it one by one here, and in order to do that, we have to find the centroid for each rectangle. It's just at the center, so here's the centroid for rectangle 1, centroid for rectangle 2, and centroid for rectangle 3. Based on these tables, these are the things that we have to compute in order to obtain the centroid. So I'm going to use rectangle 1 as an example on how to compute each of the values. So for area, for rectangle 1, the base 0.025 times the height 0.6 in meter is equal to 0.017 meter square. The x bar is half of the base, which equals to 0.0125 meter, and for y bar it is half of the height, which equals to 0.34 meter. The first moment area with respect to the y-axis is equal to 2.125 times 10 to the power of negative 4 meter cube, and the first moment area with respect to the x-axis is equal to 5.78 times 10 to the power of negative 3 meter cube. Similar calculations are performed for rectangle 2 and 3. Finally, we compute the x and y coordinates of the centroid by dividing the first moment by the total area. The location of the centroid is somewhere here, which the x-coordinate equals to 0.11 meter and the y-coordinate equals to 0.38 meter.
So, basically, if you want to find the moment of inertia, we need to use the formula that we already learned, which is moment of inertia equals to moment of inertia of a central axis plus cross-sectional area, which is A, and square of distance D between both axes. So, firstly, we calculate the area of every system as shown in the table, and we calculate the Ix of each component using b to the power of 3 divided by 12. Furthermore, we calculate the cross-sectional area and square distance between both axes of every component to find the total value of it respectively. But before that, we need to calculate the distance of every component, so we use the sum of the y-axis value minus the value of y-axis of a specific component, like the first component, 0.3x minus 0.34 equals to 0.04, where 0.3x is the total y times area over area, minus with the centroid between this and this. So we obtain the information from the question 1. Otherwise, in order for us to complete the calculation, we need to calculate the cross-sectional area multiplied with the square of the distance between the x-axis. After we finish all the calculation, we use the sum up of the value by the following equation, which is Ix equals to Ixc plus AD squared. And the value moment of inertia about the x-axis is 0.72 times 10 to the power of negative 3 m to the power of 4. So now, we need to calculate the radius of gyration, which is kx. So for radius, so if you want to find the radius of gyration, we need to use the answer for moment of inertia that we find before, over total of area and then square root. So we use the value for moment of inertia, which is 1.72 times 10 to the power of negative 3 over total of area, which is 0.0382. The answer, which is 0.045.